what is going on? It is a new month, Friday, July 1st, 2022, and half the year is over. Wow. Okay, what a year it's been. A lot has gone on. If you've been paying attention to the news, there's been trials, there's been courts, there's been lots of other stuff happening, and yeah, it's now summertime. We've been 10 days into summer. We're going strong into the season. It's hot like every day here, and yeah, I'm excited. And try not to spend all day indoors doing algorithms, but obviously, if you have some kind of interview prep you're doing, or if you want to, just be sharpening your skills all summer, hey, it is the time between school sessions, for instance, right? Anyway, enough of that. So welcome to Shaft Algo Guy. If you like my videos, please like, subscribe, and comment. It helps me do my videos better and motivates me to continue. And so today we're going to be doing a problem, 2144, called minimum cost of buying candies with a discount. I like this problem. And so let's get to the statement. A shop is selling candies at a discount. For every 2 candies sold, the shop gives a third candy for free. The customer can choose any candies to take away for free as long as the cost of the chosen candy is less than or equal to the minimum cost of the 2 candies bought. For example, if there are 4 candies with costs 1, 2, 3, and 4, and the customer buys with costs 2 and 3, then they can take the candy with cost 1 for free, but not the candy of cost 4. Given a zero-indexed integer array cost, where the cost of I denotes the cost of the ith candy, return the minimum cost of buying all the candies. Okay, what a statement, right? Okay, so there's a lot of words here, and so let's look at the examples. So the cost array, we're given an array of candies, right? Not necessarily in sorted order, see, but we're given an array, 1, 2, 3. And the minimum cost is 5, because if we take away 2 and 3, then we can remove 1 for free. So the cost of, if we purchase 2 and 3, that's 5. So we buy the candies at cost 2 and 3 and take the candy with cost 1 for free. The total cost is 2 plus 3 equals 5. And the only way we can buy the candies is this. Note, we can't buy the candies with cost 1 and 3 and then take the candy with cost 2 for free, because the candy would cost 1 and 3. 2 is greater than 1, which is one of the components of the previously purchased candy. So remember this line here, the minimum cost of the 2 candies bought. Okay, minimum of the cost. This would have been better worded as the minimum of the cost of the 2 candies bought. Okay, so it's not like smaller than the total sum. It's the smaller of. It has to be less than or equal to the 2 components that were gone into the original candy purchase. Okay. In this case, which is more demonstrative of the problem, we have 6, 5, 7, 9, 2, 2. The total cost is 23. The way in which we can get the minimum cost is described below. Buy the candies would cost 9 and 7. We take the candy with 6 for free, so 9 and 7. Purchase, eliminate 6. We buy the candies would cost 5 and 2. 5 and 2 purchase. We eliminate 2 because 2 is less than or equal to 2. Take the remaining last candies with the cost of 2 for free. Hence, the minimum cost to buy all the candies is 9 plus 7 plus 5 plus 2 equals 23. Okay, and if you have only 2 candies, then you have to sum just those candies up, or 1 candy. Okay, so how do we approach this problem? So, a first thing you might think is like, well, some kind of brute force way of doing this is that we can we could purchase we could try all the pairs of candies that are legal to purchase and legal to remove, right? So, for example, I could buy 5 and 9 and then remove 2. I can buy 7 and 9 and remove 5 or 6 or 2. I can buy 7 and 6 and remove 5 and 2 and 2. And try all of those iterations. And if you're familiar with how DFS works, or backtracking, this would be a backtracking type problem, and this would be pretty cost intensive, right? Because this array could be huge. I mean, if you look at the cost length, 100, right? We could have hundreds of pairs, and we can have an exponential number of choices we could make to remove candies. So we don't want to necessarily do things that way, because it would just be super slow. So what do we do? Well, we can the good thing is we have certain words we want to focus on: minimum, right? So how do we minimize things, right? We want to minimize things. The first thing you might think is, well, how can we get rid of the largest contributions, right? So why is this, in this case, 9, 7, 5, and 2 are the choices? Because 9 and 7, what's the next largest number that comes after 9 and 7 that I can remove? That would be 6, right? I don't want to remove 5 because 6 is larger than 5, and so 6 would contribute more to reducing the minimum cost. And then 5 and 2, I would remove 2 because that's the only choice left. But let's think about that. We always want to remove the largest choice from the array that we can. So if we look at this, what does this bring into mind? Well, how can we always find the largest number to remove, right? Well, let's look at this. What do we know? The largest number to remove has to be less than or equal to the smaller of the 2 candies that were purchased prior. So could I not just sort these guys, right? So what if I were to sort these guys? 9, 7, 6, 5, 9, 7, 6, 5, 2, and 2, and therefore I could get rid of 9 and I can get rid of 6, right? Right away, I know that the next number that I have to get rid of is 6, and then right here, the next number I know I have to get rid of is 2, and then I can get the answer. That's equal to 23. And the same goes for the first problem. So maybe that's a strategy that we can try out. So how do we go about doing this? Well, the first thing that comes to mind, sorting. We can easily sort these candies, but I want to try a priority queue or a heap solution, right? Because the heap solution, you automatically get the sorting and removal pretty easily, right? And what kind of heap do I want to do? I want to do a max heap, okay? Because I want to, so this is the comparator for a max heap, right? I'd like to do this because this is, this just lets me traverse this array in that a method that I just showed you prior. So int min cost of candies. So we're going to have a minimum cost of all these candies here. All right, so this is the thing that we're going to return in the end, so we might as well put that return min cost of candies, right? And then, now that we return that minimum cost of candies for it, now what we're going to do is we're going to put everything on our heap, right? So if you're familiar with how heaps work, great. If not, refresh your memory on that. But this candy heap is going to order elements as I add to the heap in log n time, right, for each insertion, and n log n because I have n candies that I need to add to this heap. So now that we have our candies added to the heap, what do? Well, it's just a matter of just going through our heap, right? And now, remember, I'm going to account for the case where our heap is of a size greater than 3. And if it's not, then remember, all I'm doing is just adding these candies together. So I have this candy heap here. I'm going to just, if it's greater than 3, right? What we do is min cost of candies and we just poll. This is if it's less than 3, not greater than 3, right? Because then all we're doing is polling. Else, now the standard case is we just add the 2 candies, and we remove this 3rd candy. This poll is not contributing to the final cost, and let's run it. Candy head. That's the answer, and There we go. We got it. Okay, great. So thank you for watching, and that's your